Okay, so hello, I'm Csaba from the Codex team. This is a joint work with my colleagues Leonardo and Dimitri, both from the Codex storage team. This is also work which is received an Ethereum Foundation grant. So we would like to thank for the Ethereum Foundation and for the collaboration that we have. So I will be speaking about data availability sampling. As an outline, I will be going through kind of five fast topics. First, I will speak about scaling Ethereum. Then I will introduce sharding and how sampling is done. Then I will, so basically dunk sharding. Then I will look at the networking perspective behind this, and then our simulator from which we are deriving results. So scaling Ethereum. So everything starts with the desire to scale Ethereum, right? Today we have something like 15 transactions per second, and this is how we measure the speed of a blockchain, and we would like to have more. How much more is a good question. Here I was putting 15K, but tens of Ks of transactions per second. And the scaling problem is partly solved, right? We have rollups, and there is a roadmap to introduce rollups, but rollups should still store data on layer 1. So we can partly solved, partly not, because layer 1 still have its blocks, and these blocks are still somehow limited. So at the end of the day, what we want to scale is the layer 1 blocks, which are now around 100, 120 kilobytes in size. So let's scale the blocks. But how much we can scale the blocks? And that's a good question to which we don't have an easy answer. Or let's say we have easy answers to scale the blocks when we are scaling resources, if we are not using small nodes, home staking, but we are going data center. But Ethereum is ambitious, and they definitely don't want to do that, also because that would compromise decentralization. So how much you can scale blocks if you are not doing that, if you are still doing home staking and blocks are getting to these nodes. So we don't know how much we can scale blocks. There was an experiment with the Ethereum Foundation to test the capacity of the real mainnet. Now testing on mainnet is not that easy. So they were creating large transactions. They have submitted these transactions, paid a fee. These were getting into large blocks. Then these large blocks were finalized. So we know that a block of 1 megabyte can be finalized, and that's a nice result. But that would be a bit of a waste to do just that. So they did more. They were setting up nodes which were measuring. So there were metrics, many metrics. But what is interesting for us is block propagation latency. So there were nodes in the network, a few of them, each client implementation actually running a few nodes, which were measuring the block propagation latency of these nodes. And what you see below is a dashboard showing a timeline, and where you see on the figure below the red lines, those are blocks which have a bigger size. So those are blocks in which there are these transactions. And you kind of see that there is a correlation, right? Where there are those latencies are a bit bigger. But that's a kind of a correlation. So we did some work to actually correlate this data with block size, and to see how the propagation latency, the diffusion of the block in the network, depends on the block size. Now, for this, we took data from there and from other sources, and we came to this. So how you read such a figure? So let's look at the blue curve. The blue curve is showing small blocks, so small blocks between 0 and 32 kilobytes. And a point on the blue curve, let's say the 2000 line, that's 2 seconds. If you go up, you see that 95-ish% of the blocks of the measurements were below this. So we measured in several places, measured for several blocks, and 95% of the measurements were below this. So you can say that 95% of the arrivals are before that, and then others are after that. The problem is that if you go larger with the block size, you see that time is increasing. And the other problem is that there is a deadline, which I was not showing here, but 4 seconds is a deadline. And while here it seems like everyone is meeting that deadline, you see that small percentage on the top, which is not meeting the deadline. And then you could imagine how, if you would increase the block size, these curves would shift to the right, and you would be in trouble. So, so we know that we can scale block size a little bit, but not too much. So we can do different things. We can try to optimize the protocol, and there was a very nice presentation on that yesterday from my colleague, which you can find here. But this is not what we want to speak about now. We want to speak about another approach, which is sharding and sampling. So what if we want to scale beyond the single block size limitation? What if most nodes have no chance to download the block because they just don't have the resources? So we should look at why we were downloading the block. And there were two kind of independent reasons to download the block before. One is that nodes were verifying the block. And the other one is that nodes were having the block, thus they were having the data, thus they were knowing that the data is available. So after data sharding, you will not have these. But nodes don't really need the block because the data which is inside, the rollup data, is not something they should interpret. So they don't really need it. And they don't have the block, so they don't have data availability, they don't know about it, so they should do something about this. And this is what they do. We are segmenting the block, and they are sampling that block. And this is what we are speaking about. So how you segment and sample the block? Well, that's easy. Segment the block, choose a piece, download that small piece from someone, and if you got that, you kind of know that with some probability that is the block. If you have k segments and you download one, it's 1 over k. If you download s, it's s over k. Nice linear. The problem is if there's just one missing, you have a low probability of figuring that out. So you do more. You do erasure coding. So you segment, extend, and then sample. So we use erasure coding in which we extend the data. We had the 4 segments. We are extending it to 8 segments. And now the property that we have is any 4 is enough. So if we know that if there are at least 4 blocks available, 4 segments available, then the block is available. Now, if you sample, you know much more. If you sample 1, you know with half probability. If you sample twice, you know with 3/4 of probability, etc., that the block is available. But that's actually still not enough. Because when I was saying we are extending data with erasure coding, you were believing me that we were extending data with erasure coding, but no one is guaranteeing that. So when we are extending data with erasure coding, the block might be extended with garbage, and then you are sampling, you are downloading that garbage, and you say, yeah, the block is good. I could reconstruct it. But then when you try to reconstruct it, you would figure out that you cannot reconstruct it, so it's actually not available. So we need to prove that the erasure coding is actually good. So we use KZG commitments over the same polynomial, which is used for the read-Solomon encoding, the erasure coding, so that the actual erasure extension is proven. So when you have the commitment, you have the segment, and you have the proof, this is self-contained, and this is telling you that this is a good one. So you can actually sample again. So this would be good, but this is still not enough. We have a one-dimensional read-Solomon code, which is extending, but it has a problem. The problem is that when you want to repair, you need all 4 chunks to get the other ones. So you basically, when you would need to repair, you would have to download the block. So you could easily get into a situation where you cannot repair because you don't have the bandwidth, and it would be a chicken and egg problem. But you can do something else. You can do a 2-dimensional read-Solomon encoding, a 2-dimensional extension, which has this property, which I'm not going too much in detail, is that you can repair from partial data. So you can repair any row or any column on that structure below. And so you just sample, and if something is missing, a row or a column can be repaired. Now I know this was very fast, and there's more. So this is the actual concrete structure of dunk sharding as it is envisioned now, just to put some numbers behind it. So we have 32 megabytes of data in a block, and this is just roll-up data, which is segmented to 256 times 256 segments, so it's 64,000 segments. Each segment is 500 bytes. And then you are extending this structure to 512 times 512, so you have lots of segments. And then there are KZG commitments behind this, which is actually quite computationally intensive to calculate. Overall, you have something, you started from 32 megabytes, and you are arriving to 140 megabytes each 12 seconds to distribute, but not distribute fully. So just a quick reminder on availability. So I was saying we can repair on the column and on the row. So what does this mean? What does this mean? Is this block available? if those segments are available and the others are not. And if you would sample, you would most probably say, no, it's not available, because we would most probably hit on something which is not there. But if you are repairing and sampling, then you would say, yes, it's available. So this is a block which is available. If you are sampling it at the wrong time, it's not. But your sampling would say, yes, it's available, and it is available. Now this is another one. Is this available or not available? Again, we have 25% of the data. And yes, it's available. You can repair it. Is this available? And you would say, yeah, you have lots of data. This should be available. But actually, it is not. If you look at it, there is in the upper left side of the black thingy, which is missing, you could put anything there and you could repair it. So it cannot be repairable because there's a point where you could put anything. And in fact, you cannot do a repair. There is no line or column which has at least half of the data, so you are stuck. And the data is not available, and where I have the N, that data is missing from the original. So you have a missing thing. That might be a transaction which is blowing up your rollup. So this is definitely not available. Is this available? This is definitely not available, right? You don't have enough data for this to be available. You have less data than the original block, so it cannot be available. Well, you could do some repairing, but still it's not available. Okay, so now we understood what is having a block, extending it, and sampling it, but this was all kind of very theoretical. We should do it in the network, right? All these things should go on the network. So what's happening on the network while we are doing this? So how we check data availability over the network? And here I think I should remind you that there are different actors in the network. There are validators and there are full nodes, and they have different goals. The check is kind of a first line of defense and a second line of defense. So validators, they are the ones generating the attestations, and they are the first line of defense. If there are not enough attestations, the block will not be part of the chain. And actually, many blockchains are happy with this, but Ethereum is ambitious here as well, and they say, this is not enough. We need the second line of defense. We need also the full nodes to do sampling to figure out with very high probability if the data is not available, even if the validators did something nasty. So we have first and second line of defense, and then we need a system which is serving all this. So how does this work? First of all, maybe I should note that we have here builder proposal separation. So you have a block builder. And this is building that huge structure. And then it is cutting it into rows and columns, and it is sending down specific rows and columns to the validators. Actually, each validator is choosing some rows and some columns, let's say 2 rows and 2 columns, and say, I'm checking only those. And I'm checking those rows and those columns, and if those are fine, I'm signing. But that's only for the validators. Then there are the full nodes. So for them to sample, we need something to sample from, and it cannot be the block builder. So the data is uploaded into a DHT, a distributed hash table, and then the full nodes are sampling from that. And then on top of all this, we need repair. So it's quite complex. Today I will focus on the first part, which is the dissemination of samples to validators, which is complex enough. So what happens here from builders to validators? We have, say, 2 lines or rows selected by each validator. And we have a dissemination, some reliable, robust, decentralized, published subtype mechanism, which is sending the data from the builder to the validators interested in those specific things. Let's say we have, actually now we have more, but we have 500,000 validators. We have something like 8,000 beacon nodes behind which there are these 500,000 validators. We have a large amount of segments. We have many rows. And actually, we have 4 seconds to do all this distribution of data. So how do you do this? We use something similar to what was used before. We use, I was saying, a gossip sub-like protocol. It's kind of gossip sub. It's not exactly the same, and it's not yet clear exactly, but we are studying it. So what you have seen before was the block, or the big block, sent to all beacon nodes, behind which there could be one or many validators, in one gossip subchannel. And then in the system, we have other gossip subchannels, so they call topics. So we have other gossip subtopics. We have something like 67, 64 plus a few. Here we would have 1,024 gossip subtopics, crisscrossing the beacon nodes and sending down rows and columns to them. So this would be an example of one gossip subtopic, which is column number 243, and imagine 1,000 of these crisscrossing. We like gossip sub because it's robust, it's reliable. Gossip sub, for those who don't know it, is pushing data to many neighbors, so it's forming a mesh, a graph with each node having 6 or 8 neighbors, and when it receives the data, it's pushing to all of them. And then it has another mechanism, which is it is telling other nodes randomly what data it has, so others can ask for it. This is the pool. And then it is doing the sending over TCP, so when it sends reliably. It also has some downsides. It has lots of duplicates, and it's not yet ready for large messages. As we have seen, there are improvements. The important things to note here is that here we have 2 other reliability mechanisms. So we have the mesh, as we said, in which the data is pushed. We have the gossip, so for pulling data. When data is passing from one node to another one, it's reliably passed using TCP. And then we have the read Solomon code. The read Solomon code means that we can, when we are sending a row, it's enough to send half of it. It doesn't even matter which half. So I can just send some of the segments from that row, and the other side, if it has enough, can restore the whole row. And then we have another mechanism, because we have the rows and the columns. So if you receive something on a row, then you can switch it on the column and send it on the column. So it is a complex system which has 5 reliability mechanisms, and we don't know really how to play it, so there's lots of things to study, which we like. And that's why we are building a simulator. So the simulator is to simulate this sharding and data variable assembling. You can find it there. It is simulating the DS encoding. Obviously, it's not doing it because it doesn't have to do the erasure coding, or it doesn't have to do the proofs. And then it simulates the dissemination to validators. It simulates the 1,000 gossip subchannels. It is not doing yet the DHT and the sampling. It's highly configurable, so you can define simulations and study things like, what if I would have much more nodes? What if I would have fewer nodes? What if I have strong nodes, institutional stakers? What if I have home stakers? How many validators are these running? How I'm configuring my gossip sub? What is the degree of neighborhood? What if there are failures? What is the network bandwidth? And then many other things. So it's quite easy to configure. It's basically Python code. So you just set the number of nodes, type of nodes, bandwidths, validators in a configuration file. And you can also set up studies. So you can set up range studies from this to that parameter, and then it explores the whole simulation space. So when you do a single simulation run, this is what you see. So this is an example. There's one builder, and let's suppose it has 5,000 megabits per second link. It's kind of reasonable to assume with the builders that are today. And let's say we have 7,000 nodes, of which 5,400 are, I was calling them class 1. This is basically home stakers. So a home staker was putting in its 32 E's, and it's running its one validator behind one node. And it has, let's say, a 50 megabits per second uplink. And then we have a bunch of nodes which are institutional stakers. They are running a beacon node, and behind the beacon node, there are a bunch of validators, let's say 500. We could randomize these numbers, but it wouldn't add too much to the simulation. So we are just doing these 2 classes. And let's say they also have 5 gigabits per second links. And then you start simulating. and these are the curves that you get. So the most interesting one is on the top. This is telling you, well, the most interesting is on the bottom, which is the time. So you have the time axis, and then you have evolution of different things in time. And the most interesting thing is on the top, of which the most interesting thing is the green one. The green one, which is telling you how validators start to validate, but nothing happens. And at one point, basically everyone is validating, and the block is fully validated. The blue that you see is kind of progress in segments received. So we are sending segments, and we are randomizing them. So we are sending them down one by one on these links on all the 1,000 topics. And nodes are receiving segments, but no one has enough to validate. And at one point, basically everyone has enough. And this is kind of a nice property of the system, that there is this changeover property. And then there's the orange curve, which is measuring how many nodes are ready. So what you see at the end there is basically nodes. Those are home stakers, which are validating a bit later in this specific scenario. And then we are measuring other things. We are measuring the traffic utilization, how many duplicates are, so useless traffic is generated by the system because of gossip sub, and so on and so forth. But the nice thing is, according to this simulation, it finishes in less than a second, right? Now, it finishes with less than a second with many simplifying assumptions, of which, again, if you go to the talk on gossip sub that I was referencing before, you can see many details on that. But we are having some simplifying assumptions on the graph, on TCP slow start, and on latencies. So let's take more conservative numbers. We change the uplink and bandwidth to 1 gigabit per second. And then you are distributing in 1 second. Still very good. And you can do other studies. So this study is looking at, on the left side, you see the figure that we had previously. So what if the system is doing the distribution, sending individual segments, randomizing them, moving them from rows to columns, and doing all the things that we could come out with. On the right side, there is a simpler version of the system, in which on these 1,000 rows and columns, you are sending messages which are entire rows or columns. Well, actually half rows and columns, because you don't have to send the whole thing. But you are not sending individual small messages. And you become slower, as we would expect. Or you can do other interesting studies. On the top, you have a situation when the builder was releasing just enough segments. So just enough segments released, and you see the blue order curves going to 1.0. Below, almost enough segments released. We have seen that case, right? The data is not available. There is something missing. And in this case, we want the system to notice it. And that's what we see there. 75% of the segments actually arrive. So not C segments, but actually there are few validations. Validations are well below. And this is what we wanted. So to conclude, here we are looking at dunk sharding, basically. But we are a team working on correct storage. And we do this because there are many things in common that we can learn from. So we are using in correct storage erasure coding, like in dunk sharding, and studying what's the best way to do it. We both use sublinear verification with the sampling, actually, in different ways, but we both use sublinear verification. We both use the libp2p stack. And even more importantly, this is important for us because there are lots of intuition in both systems which are mutually useful. There are differences as well. Dunk shard is focusing on data availability. In storage, we are focusing on data durability. Dunk sharding doesn't need long-term storage. You just need to prove that things were released, and that's fine, and you are not doing this for long-term. We are doing long-term storage. Dunk sharding is doing interactive sampling. Nodes are going and sampling. We are doing snark-based verification, but both are sublinear verification. Dunk sharding is using fixed block size. We are accepting all data sets. But overall, it's very useful for us. So finally, to conclude, we are building this open source simulator. We are happy if you come and try and contribute. We are exploring multiple design for DAS. We are exploring the DAS parameter space to understand what will happen if situation changes this way and that way. And we are building a long-term storage with codecs. Thank you.
One question?
Thank you.